looking at Jordan's lemma, I believe, right? Okay, good. So we're going to look at two corollaries, so these are also in your exercises, in your assignments now. That's just the background. Sorry, I've caught a bit of a cold, so excuse me for that. Let's write down the two lemmas. So the first, I think I wrote down the statement of lemma 2.2, right, in your notes. Is that where we stopped?
Yes.
Yeah? Okay. So let's do lemma 2.3. So this says that it's essentially the same for any two projectors, pi 0, pi 1. Okay. Let Si be a two-dimensional subspace as described in lemma 2.2. Okay. So you can write it in a block diagonal form, right? So Si was one of those subspaces, and then suppose phi 0 and phi 1. So let these be the two eigenvectors. Of omega pi 0 plus 1 minus omega pi 1 that span Si. Okay. With eigenvalues lambda 0 and lambda 1 respectively. Okay. So then it holds that lambda 0 plus lambda 1 equals 1. Okay, so the statement is that if you had the projectors pi 0, pi 1, you write it in that special subspace form. Then for every two-dimensional subspace, you consider two vectors that are eigenvectors for this subspace with eigenvalues lambda 0, lambda 1. Then these eigenvalues will sum to 1. Okay, that is the lemma. And let's also quickly look at the proof because it's kind of straightforward. So restrict to Si. Okay, so I'll take the omega equals half case. The general case is essentially the same. Okay, so you restrict to Si, and then lambda 0 plus lambda 1 in this case you can write as trace of pi 0 Si plus pi 1 Si by 2. Right? Because eigenvectors, and we're just writing them as okay, and then so this one can write as 1 by cos square, 1 by sine square, which is 1. Okay. Okay, and this follows from the form that we had for these pi 0, pi 1. Is the proof clear?
So restricted to Si, what do you mean?
Oh, so the projector, but I'm looking at its action on Si only.
So you ignore the other part, or
Yeah. When I'm writing this notation, huh?
you put the other part 0, or
Yeah, you're restricting your, like when I'm writing trace, I'm only thinking of, vectors in Si. That's, because otherwise this is a big object, right? This is a potentially huge object. So I'm just restricting to this object to the two-dimensional subspace, and then all the operations are in this two-dimensional subspace. Okay.
And you use previous lemma that pi 0 si is 1 0 0 0.
Yeah, yeah. So then you use the characterization here. You use this 1 0 0 0, and the other one was, there was like cos square, sine square, and then there were cos sine, right? So then you're just tracing it, so you'll get cos square plus sine square. This would be 1. You sum it half, and this is just because these are the eigenvalues of these two vectors, and so you're just okay. So that's fine. Sorry, yeah, it's probably too elementary for you guys, but so it's good. And then the corollary is the following. So for any two projectors, pi 0, pi 1, let phi 0 and phi 1 be eigenvectors. Eigenvectors is the same, right, of omega pi 0 plus 1 minus omega pi 1 with eigenvalues lambda 0, lambda 1. Okay. So now if lambda 0 plus lambda 1 is not equal to 1, okay, and lambda 0 is distinct from lambda 1, then one gets the following. One gets phi 0, pi 0, phi 1 is the same as phi 0, pi 1, phi 1, and this is 0. Okay. So is the statement clear? It's just trying to show that if you somehow know that the eigenvalues are distinct and they don't sum to 1, then the inner product on pi 0 with different vectors is going to disappear. And they use it for showing, like, when they are in the proof, the way we'll use it is that off-diagonal terms are going to disappear when we're doing the analysis. So it's a very useful property to have.
2.3 sounds strange. So this means that the rank of this projector, omega pi 0 plus 1 minus omega pi 1, is quite high. Because for each subspace, you have the sum of eigenvalues to be 1.
Yeah.
Right?
Yeah.
So if they are like, say, n subspaces,
Yeah.
then the rank of these projectors are n.
Yeah.
But you said any two projectors. So
Yeah, but you're restricting to the subspace. So they would. So if you're thinking of a rank 1 projector, for example, then you would.
For all i's, right?
For all two-dimensional subspaces, yeah.
Yes,
So
for example, if there are 4 subspaces, then rank seems to be at least 8.
yeah, yeah. Then it's correct. But like if you're starting with something which is low rank, then you won't have so many two-dimensional subspaces. That's essentially what it means, right? You'll just have one-dimensional subspaces. Yeah. Like for example, just add zeros, right? Like it's still a projector, and then those will just be one-dimensional subspaces. So,
SI number of SIs will change.
yeah, yeah. Mm.
These subspaces could also be one dimensional. It's at most two dimensional.
But the lemma is only for two-dimensional subspaces. Yeah. This characterization only works for two-dimensional subspaces. Yeah.
It is not necessary that projectors have a two-dimensional subspace.
Yeah, it may not even. Yeah, yeah. Exactly. Yeah. Okay. Any other questions? Is it okay? Yeah. This should be very clear. Right? This is just simple algebra. Like people still look a bit confused. I don't know why. It's fine, right? If something's not clear, ask. Okay. There's no.
Things are very strange, actually, but they are true. So here, phi 0 and phi 1, there was no reason that phi 0 has support on pi 0, or they have a disjoint support, but it is true.
Phi 0, phi 1 have support on pi 0. They're essentially, I think, in the same sense as this. I mean, you're thinking of them in the same sense. You're not restricting the subspace, you're right, so they can be outside. That's how, I mean, of course, if they were in the same subspace, they would sum to 1. So obviously we'll use the fact that that's how you'll get orthogonality basically. That is basically a preempting the proof. So let's do the proof. So the proof says if lambda 0 is, so plus lambda 1 is not equal to 1, then, so as Uttam Bhai was essentially preempting, lemma 2.3 says that phi 0 and phi 1, right, cannot be in the same Jordan block. Right. So that was one. And the second is pi 0, phi 0 stays in the same Jordan block, right, by the previous lemma, the one before, 2.2, right? Okay, and so this implies that phi 0 is orthogonal to phi 1. Orthogonal to phi 1. Oh, sorry, pi 0, phi 0 is orthogonal to phi 1. Okay, so that completes the proof.
Do you see the second?
Oh, because these guys, I mean, this is following from the previous characterization, right? That you have these blocks, and the pi's will preserve the blocks. So if you have any vector in a block, it will stay in the block. And lemma 2.3 tells you that if the sum is not 1, then they have to be in different blocks, right? And so then you get that they stay orthogonal. Okay. Very nice. Now there's going to be one more lemma which I have given as assignment, so maybe, and we'll probably need it towards the end. So what I'm going to do is I'm going to defer this, and hopefully you would have read it by the time you need it, and it will not be that big of an issue. That is actually a very sort of strong statement, but we'll come to it when we come to it. Okay, so I think last time we managed to show that we gave a construction, right, last time, and we said that it is secure as long as that strengthened monogamy of entanglement game is secure, right? But we did not prove that strengthened monogamy of entanglement game is secure for coset state, so we're going to do that today. Yeah, let me just make sure I haven't missed anything from. Yeah, no, good. Okay, so we're going to need hybrid 0. So let me write down the game that we looked at last time. Okay, so here's, yeah, so since we'll need all the hybrids, let me write the hybrids on the left side. Hopefully this will be enough. Okay, so this is, so we're basically trying to prove the statement that we had, which was theorem, oh shoot. Okay. Sorry, I was about to write down the weaker game, so let's write down the stronger game. So yeah, we're trying to prove theorem 4.8. Okay, theorem 4.8. Okay, so I'm just going to write it informally now because we have the formal statement written. So we're going to say that the advantage of the following game with ABC for any ABC that make poly many queries is at most half plus negligible. Okay, and what is the game? So the game is the following. So the game is that there's a challenger, okay, there's an adversary. The adversary sends a delta of length n, okay, so it's a string of length n depends on the security parameter, so let's write it. And then A is a subspace of f2 to lambda of dimension lambda by 2. SS prime belong to the canonical string, right, for A cross canonical string for A perp, right, and canonical string mean it will be the shortest lexicographically, right, so we don't have to worry about these things later. And then you pick B uniformly at random, you compute omega, which is evaluation of the random oracle XORed with the message, with the input that was sent by the adversary depending on whether B is 0 or 1. And then one sends the coset state together with this omega, right, that we computed here. And the adversary is allowed to output some bipartite state BC, which goes to Alice and Bob, Bob and Charlie. They also get the description of the state, not the state, the subspace, right? And this was also somebody had asked, I think you had asked, I don't remember. Somebody had asked that why is it that, what is the difference between what A can do and what BNC can do? So it's basically the fact that BNC received the decryption key, as Ariman had pointed out. Okay, so that's the key difference. So they both get this, and the objective for both of them is to output B sub B or B sub C, right? So that's the challenger. Okay. And then you output 1, right? If you get, so output equals accept if BB equals BC equals B, and you reject otherwise, right? And that's the output. And advantage is basically just the output being 1. Okay. Okay, so that's the original game. Now we have to prove this. So what we're going to do is we're going to, as usual, construct some hybrids. So let's construct the hybrids. Yeah, it looks like we might actually be able to finish this today. That would be very nice. Okay, so this is going to be probably the most technical part of this this lecture, because now we've put all the pieces and we've collected all the pieces. We'll do the proof now. So if something is not clear, if you feel I'm going fast, tell me, because the feedback last time was that things are going a little bit fast. So slow me down when you feel like you're getting lost. There's no point in covering things if you're not following, right? Okay. So this is also what we're going to call hybrid 0. Okay. So now hybrid 1. So this is going to be the same, right, as hybrid 0, except, so it's very similar. A is going to be reprogrammed. Sorry, H is reprogrammed. Yeah, maybe let's just say H is reprogrammed for A. Okay, so it's reprogrammed, so okay. It was sort of implicit that everyone has access to the random oracle. I didn't write it explicitly. So now what we're going to do is we're going to change the random oracle that A has access to. Okay. So what we're going to do is we're going to change the oracle to HSS prime, which is defined as follows, which is the following. So HSS prime, ZZ prime is going to be a random string U if Z equals S, Z prime equals S prime, and it would be H ZZ prime else, right, where U is uniformly chosen and has length n. Okay, because remember the random oracle that we were using was also of length n, right? The output was also of length n. Okay. So one might ask why we are doing this, okay, and the reason is, yeah. So we've not done much. We've just reprogrammed the random oracle at the secret string SS prime. Okay, everything else is the same. And why we are doing this is because we are making the adversary A not have any correlation with the random oracle at SS prime. That's like, so it's nothing very deep. You're just, I mean, you're replacing a random input with a random input. That's why I'm trying to give you a justification, because it was already random. It's just that now it becomes independent of what the actual value of the random oracle was. Okay, so there's nothing very deep happening. So this is fine. This was like a relatively simple modification. And now let's write down hybrid 2. This one's a bit more involved. I mean, the changes are a bit more drastic. Okay, so this is the challenger. The challenger is going to sample uniformly random. So subspace A of f to the lambda of dimension lambda by 2. Okay, 2 vectors SS prime in CS, what was it? Canonical strings. Okay, so far it's essentially the same. Okay, B is chosen uniformly. Okay, and now the new thing. Okay, so now R is chosen from the set of all n-bit strings. Okay, and it defines the following oracle. So it defines the oracle H sup B SS prime as follows. Okay, so this is where your tech overview would sort of help you with what is going on. So remember, in the tech overview we had the challenge mode and the independent mode, right, where you were asking the same B or you're asking different Bs. So this is kind of what we're formalizing now. So it's going to be R XORed with B dot delta. Okay, if Z equals S, Z prime equals S prime. Okay, and H of ZZ prime otherwise. Okay, so in the original one, depending on whether you had B0 or B1, you were always XORing with the random oracle evaluated at SS prime. Now you have a new random oracle which has essentially the same distribution, right, because this R was initially supposed to be H of SS prime, right, but there was a random oracle, so this was also random. So the distribution is essentially the same. But yeah, let's see how it's actually used. I don't think it's worth explaining why this choice makes sense. It will become clear. Okay, and so then this is the adversary. Okay, so the remaining part is essentially the same. So there's B, C, you get description of A, description of A. Adversary B, adversary C. Okay, and after output B sub B, B sub C, then the rest is the same. Okay, so the outcome is accept when B sub B equals B sub C equals B. Okay, reject otherwise. Okay, so yeah, this is the only part that's essentially new, and The other difference is that these guys get access to, yes, let me just write A, B, C, get access to, yeah, okay, so let's just say BC get access to H to the B SS prime, okay, and A gets access to H SS prime as we had defined earlier. Okay, so what we're doing is we're changing the oracles that you're giving to the different adversaries, but we're doing it in steps. So in the first step, we changed the oracle that was given to A, and the next step, we're changing the oracle that's given to B and C. And yeah, and we'll basically show that all these hybrids are going to have the same success probability. Okay, so hybrid 1, maybe I can.
How do you ensure that they have different kind of oracles?
Oh, because the way, okay, so that's a good question, but it's much more widespread and much more general than just this setting. So when you're given access to these adversaries, you're thinking that you have some kind of a code that you have access to, right? And this code is going to invoke the random oracle, because the only way to learn the value of a random oracle is by querying it at a certain register. So then when it does make the query, then you replace the answer with whatever you want it to. So basically you simulate the random oracle for the adversary, and you show that the adversary is able to do something bad, or able to solve a hard problem by doing that.
So this strengthens in some sense.
So what you have is that, suppose you have an adversary A, right? And suppose you have some guarantees on.
If this is a weaker access or a stronger access.
It's just the way the random oracles, the methodology works. So the way it works usually is that you have some, you have some algorithm, right? And the whole point of writing this as a random oracle, or any oracle for that matter, is that the only way A can access any information about H is by querying H. Okay. So what you do is so if you think of it as a circuit, right? So there is a circuit, and every now and then it will have these gates which are going to run the random oracle, right? So what you do is you embed the whole thing in a bigger circuit, okay, and say you want it to be efficient in some sense, like it makes only poly many queries, whatever. So you can do that, and then in the new circuit, you're allowed to change, the response to the random oracle. Like you're allowed to do whatever you want, as long as you can prove that this new circuit solves some difficult problem that is enough to show that such an adversary A could not exist. That works with the random.
Simpler question. I'm thinking that how can I make sure that this new X, for example, H is say the oracle solves NP-hard problems. Okay.
Oh, so you're saying A to the H solves an NP-hard problem, okay?
And while the other new oracle solves simpler problems, something that is inside the NP.
New oracle, the oracle is not solving a problem, right?
No, I mean the query
A to the H
to something that cannot solve NP-hard problems. How will I make sure that?
So you start with some assumption about A to the H. Basically, you're trying to rule out what kind of A's can exist, right? So if already you're claiming that A is solving an NP-hard problem, that's good evidence that such an A cannot exist. Typically, it's harder. Typically, you have some A which is, supposedly violating some security condition, and you say I can use that A to the H in some different setting to construct some A prime algorithm, right? That will solve a hard problem. And depending on the kind of problem NP-hard problems are like problems independent of H, right, normally.
Yes.
So if you think of a problem that actually depends on H, right, like for example in this case, you're asking what is the evaluation of, you're basically trying to find SS prime, right, because somebody is using SS prime. So as long as you're finding a property of H or something related to it, then you can argue that that problem could not be solved because if it could be solved, then you have like some A prime that can solve that other problem. I don't think I'm answering your question. You still look very confused.
Maybe I'll ask later. Also, what is the assumption on H here? That what kind of random oracle? I mean, is there some assumption on it? Because
no, it's a random oracle.
It's a random oracle, right?
Yeah.
That's
Or you'd
it.
think, yeah, it's just a random oracle. You have an algorithm that queries the random oracle, and I was just saying that the answer to the problem might be encoded in H, right? Otherwise, for example, A could be solving a halting problem without querying H at all. So obviously, you cannot make any statement that depends on the fact that it's querying a random oracle. So the problem has to somehow depend on the random oracle to begin with. So that's the point I was trying to emphasize when you were saying that if it solves an NP problem, it could even solve a halting problem, but that doesn't mean I can necessarily use that to show that some question about H is being answered, which is difficult to answer. Whatever.
This looks like a weaker notion.
What looks like a weaker notion?
Yes, if it's stronger or weaker. So hybrid 2, when you like allow the challenger to manipulate what the oracle can say.
Yeah.
Yeah, weaker is stronger has to be specified.
Yeah. Like it depends on what you're trying to do, right? So here we are just saying that if you had such an oracle, or if you had such adversaries, right, and the only assumption we are making is that they were solving the problem, the specific problem in particular, by querying a random oracle, then I'm saying that I can use that to construct a new to construct some new set of adversaries, right, that will solve a harder problem.
Here my question was not.
No, I mean it's a valid question because you're trying to understand. Like for example, it's important that the algorithm I construct, whatever new algorithm I construct, it should not be making say exponentially many queries, right? Because with exponentially many queries, I could anyway have solved the problem. So you have to keep in mind. So the strong or weak would depend on what assumption you're trying to break.
And this kind of replacement is kind of trivial, so one can always do that.
It's not always trivial. So here in particular, remember that you do not know SS prime a priori, right? That's why we had to use coset states and we could not use the original BB84 state. So your question is very valid. Like what how it should not be that to modify the oracle itself I have to do some crazy
Some
code.
solution,
Yeah. So here this part we discussed when we were discussing the tech overview, that you can actually make such a substitution because you have access to membership oracles. So this is implicit, right? Like everyone has access to the membership oracles. Okay. And in particular, it can be done efficiently. Not only that's kind of the key thing, that you don't want any of your algorithms to become query inefficient or inefficient in any other way. Okay. Okay, good. So let's. Yeah. No, I think I misspoke. We only care about query efficiency. So when I'm saying, because all of these are information theoretic, except the number of queries has to be polynomial. So it can, like for example, it could solve a halting problem, but that still doesn't mean it would violate the monogamy of entanglement game. Okay. So.
So you're saying H could solve the halting problem by itself?
H is just a random oracle, so that has nothing to. A could solve a halting problem, but that doesn't mean it would violate the monogamy of entanglement game. Yeah. So even that is not enough. Basically, that's the point.
So within this hybrid, A sends the challenger delta.
Say it again.
Delta is sent by the challenger.
Yeah. So there's no. What did I do to the delta? I should have written a delta. Yeah. So there's no change in the first step. Thank you. Yeah. Okay. Any other questions?
It's like a basic question. But,
Mhm.
this random oracle model, is it the same as this common reference string?
No. So you can do more with the random oracle. So in particular, the random oracle gives you a common reference string. Well, okay, depends. There are also flavors of common reference string. So if you think that the reference string is uniformly sampled from the set of all strings. So for those of you who don't know, maybe it's good to know. So CRS is and the random oracle model. So CRS basically assumes that there is somebody who samples a uniformly random string and gives it to all the parties before the protocol begins. Okay, and the random oracle is that somebody samples a random function from the set of all functions and gives it to all the parties who can query access it. So clearly, if you have access to a random function, you can get a random string, but the other way is not obvious. And I think there are oracle separations. I don't remember them off the top of my head. Okay, so let's move on. So I'm going to erase maybe hybrid 1 as we need more space, because I don't want to erase hybrid 2 or hybrid. Yeah, let's see. Okay, so these are the hybrids, okay, and then we're going to use the following. So denote by p sub I the optimal success probability of hybrid I. Okay, which is essentially the advantage, if you like, but it's just using more compact notation. Okay, so the proof is going to be 5 lines. Okay, ready? Okay, so the first line is P0 minus P1 is at most negligible in lambda. Okay. Lemma 4.10 is P1 is exactly the same as P2. Okay. And lemma 4.11 says that P2 is at most half plus negligible. Okay. And so combining these, you get the proof. Okay, of course, we have to prove the lemma or the lemmas. So these two are actually very straightforward. So we'll look at them in a moment. We'll mostly spend our time proving lemma 4.11. Okay, so we'll mostly have to focus on this part. Maybe I can even leave it as an exercise. Oh, but I already sent out the assignments. Maybe it is in the assignments. I think it is in the assignments. Okay, let's see. Fine, let's do it. Okay, so let's start with 4.9. So 4.9 is I'm just trying to see, because we won't have enough time, so I'm trying to see if I should leave the harder part or the simpler part for you as an exercise. But yeah, maybe let's just do it, because that's okay. Okay, so lemma 4.9 says what? So 4.9 was saying that hybrid 0 and 1 have essentially the same success probability, and this is going to be like a very standard technique, so it's good to check. Oh no, of course I forgot to tell you one theorem. Shoot. Okay. Don't worry, I'll tell you the theorem. So this theorem is a very old theorem. It was essentially used, I think, in the optimality of the Grover search. So the theorem statement, so maybe you can write it down actually. Before the lemma, let's do the theorem. So theorem 2.1 says the following. So it says let A be an adversary, okay, with oracle access to H going from 01M to 01N, making at most T queries. Okay, so this is a statement about some algorithm A making queries to some oracle H. Doesn't even have to be random actually for this statement, so it's more general. I'm actually not sure. It doesn't say in the theorem, so I thought it was like a general statement. Like, in any case, it's not wrong if you assume it to be a random oracle. I'll check if it works in general. I think it works in general, but yeah, let's just assume it's a random oracle. Okay, then the following holds. So definition 1 says, let phi I be the, so define phi I to be the global state. Let phi I be the global state. Global state after making how many queries? Okay, so after A makes the ith query. Okay. So, the model that we had in mind, right, that you have a query register, you have a response register, so every algorithm is going to prepare the query register in some form and then say, okay, now apply the random or whatever oracle and get the output in the output register. So just after you get the response, okay, so after you've made the ith query, it's saying that the state of the algorithm is given by phi I. Okay, so it's making t queries, so for every query you can write phi sub I.
And algorithm will be doing something else as well.
Yeah, the algorithm is doing whatever it wants, so therefore it's like a very general statement. But obviously for every algorithm you can assume that it's pure, and you can write that the ith step, this is what's happening. And then omega sub y acting on phi I be the sum of squared amplitudes. Amplitudes in phi I of terms in which A queries H on input Y. Okay, so you look at the state, it has a query register and you're summing up the weight on all the amplitudes where the query was made on register Y. Okay, because there could be like other registers doing whatever, so you're just summing up all the weight on the register Y. Oh no, it's okay. Okay, and I'm out of space. Interesting erasing decision. Okay, so let me compress hybrid
So
one.
we are thinking of phi I as a large superposition, and you will collect the terms in which the query register is in Y.
Yeah, you collect the amplitudes for all the, because the work register, like it could be doing something internally, so the state phi I can be very complicated. So you look at only the query register and collect all the amplitudes that correspond to querying at Y. Yes, let me just quickly write hybrid one. So here A gets H SS prime, okay, and this is U if Z prime equals SS prime H else. Okay, so that's hybrid one, just for us to remember. I'll erase this now. I'll write the rest of the statement. Oh, we're running out of chalk. Very nice. Ah no, there's still a few. Good. Okay, and then we let epsilon be greater than 0, and then we let f be a subset be a set of time string pairs such that sum over I comma y in this f omega y phi I is at most epsilon square by t. Okay. So what is this saying? It's saying that suppose there's some error, right, some epsilon, and now you take a set, okay, which basically has these ordered pairs. So at every I, okay, it's a relation, so it can be more general, but like intuitively for every I, it's telling you what all y's you're looking at. Okay, so at every time step, which y is of interest to you, and you look at all the weights at that ith step that were put on the y. Okay, it's a very useful statement, so it's good to spend some time to make sure we understand what's happening. Okay, so this is the statement. Oh, sorry, this is the premise. The statement is the following. So you say, let h prime. Oh, sorry, we're still not done.
Epsilon by t or epsilon square?
Square. Yeah. There's a square here. Sorry. Epsilon square by t. And okay, so and then h prime. So we're still not done. There's the third thing. So let h prime be an oracle obtained by reprogramming h on inputs iy in f to arbitrary values. Okay, so you first found these pairs iy, okay, and at every step, like, you can use a different oracle if you want, right? It's not even saying that you have to use the same reprogrammed oracle throughout the algorithm. Every time it makes a query, you could potentially have changed the way the thing works. So you can reprogram h in at all these inputs. You could have changed the way the oracle works. But what you know is that the weight of the original algorithm on these on this set f was at most epsilon square by t. Okay, this you knew from, like, for whatever reason, that's in your premise. Okay, and so we define phi prime I as above, but with h prime. Okay, so you use a different oracle. Instead of h, you use h prime. Okay, then the trace distance between the final state of the original algorithm and the final state of the algorithm where we used h prime is going to be at most epsilon by 2. Okay. So intuitively what this is saying is that if you can somehow bound, so you can find a set, on which the query weight is bounded by some value, okay, and you change the oracle on those values, then the algorithm's output cannot be very different. Does that make sense?
You are somehow changing a low amplitude thing.
Yeah. So it's basically saying that we'll use it in the contrapositive, in the proof.
Right.
So we'll say that if the trace distance is high, like suppose for contradiction, you could distinguish it, then the weight would have been high, and if the weight is high, then I can measure the query register and find the place. And in particular, where are we reprogramming? On SS prime, right? So what we'll say is that if somehow your new algorithm, like basically we'll argue if hybrid 1 and hybrid 0 were producing different answers, right? Then it's the contrapositive of this, so for the final thing is different. And so what that would mean is that the weight on SS prime must be high or non-negligible, and so therefore if we just measure a random query with non-negligible probability, we will actually find the. Okay, that's essentially the proof of lemma, whatever the number was, that hybrid 0 and hybrid 1 is close.
Is this in real paper? This thing.
Oh shoot! Yeah, I didn't give credit to the. No, this is a very old paper.
Oh, okay.
This is BBV 97. This is a very. I think they formalized it in this way here. Maybe actually it's originally also formalized like this. I don't remember, but This is query complexity is very well studied. So some of the early techniques are, yeah. But of course, still Xandri found a way to like revolutionize it by finding this compressed oracle stuff. And but okay. Okay, so this is a very general but very basic statement. It's very useful as we just saw. Okay, so so I'm not going to prove this. I leave this as an exercise, as an application of this theorem, showing that hybrid 0 and hybrid 1 are essentially the same. Argument is just that you do the contrapositive. Okay, very good. I'll probably need a few more lectures. This is bad. Bad in the sense that I wanted to not just do this, but okay. And so we're done with 4.9. 4.10 is basically 3 lines, so let's do that as well. You guys are following, right? I'm not sure if it's making sense. Yeah, Niranjan, is it? If something's not clear, ask, because you know it's I don't know what else I can do personally to make sure it's clear. Yeah, everyone? Yeah, unfortunately, I think with these things you kind of have to go back and read it because there's just a lot going on. It's not very difficult, it's just long. So
Yeah, but with this theorem, I mean, lemma 4.9 is quite obvious. Like
yeah, lemma 4.9 is straightforward. Also, the next one is not too hard. Showing lemma 1 and hybrid 1 and hybrid 2 are the same is not very difficult because yeah, let's just do it. It's just 2 or 3 lines. Let's do it quickly. And we'll use the like all the theorems and the lemmas we have. We will put them to good use now. So
the H is reprogrammed differently.
yeah, it's essentially the same distribution actually. This one's in fact even easier. It's not very. Sorry, 4.10. 4.11 is the hard one. Okay, so it says so fix any delta and b.
Couldn't we have used this theorem to show like P0 minus P1 is also bounded negligibly directly?
Yeah, that's what I said we are not doing. P0 minus P1.
No, P0 minus P2, sorry.
P0 minus P2.
Because essentially P2 is also just
Yeah, you're skipping a step. I mean, it's just for clarity. Like you do P0, P1, then you P1, P2. Well, you could obviously, yeah, you could. Sure, exactly. Yeah, so the nice thing is that now you can actually show P1.
Probably is asking that why 4.11 is difficult. If we can prove P0 and P2 are negligible, then
No, negligibly close.
negligibly close.
then
That
we
doesn't.
can, right?
Why?
No, we need
Why are we done? No,
negligible.
why are we done? Let me ask him, right? He'll know.
P0, then P0 is already negligible and P0, P2 are also closed.
Why is P0 negligible? P0 is what we want to prove, right? Is at most
Yes,
R plus.
we will prove P0 and P2 are close by.
Yeah.
So we need to prove then one of them is negligible.
Yeah. So that's the main step, right? Like you have to show that the hybrid will. So basically, you have to show that if this hybrid wins, then somehow you can win the monogamy of entanglement game. So basically, you have to find a way to extract SS prime.
Yeah, one of the probability need to be proven half plus negligible.
Exactly. And obviously, because you know, if you could do it already with hybrid 0, you would do it, but you can't. So that's why you're going to later hybrids, right?
I said the answer is true.
Yeah, you assume the answer is already bounded. Then there's nothing to do. Exactly. Yeah, no, it happens with these long proofs. It's easy to get lost. Okay, so it says fix any delta and b. Okay, so delta and b are.
Shreyas was asking, is it answered? Interrupted.
Yeah, he was just trying to skip a step. He was saying that we can just go from P0 to P2 directly and show that they're negligibly close. the way the paper does it, it goes, it shows P0, P1 are negligibly close, and P1, P2 are in fact identical. So let's see what they're saying. So they say that, you fix delta and B, and it says then the games are identical. Okay, so then the claim is the games are identical. Games are identical. So what you do is you simply rename. So simply rename omega, which we defined here, right? So omega was HSS prime B dot delta. Oh, did I mess up? No, that's hybrid 0. Hybrid 0 is fine. Okay, so it says simply rename this to R, and because what did I do? Did I do something wrong?
Just prime as
Yeah, so okay, so I'll write down what they've written down, and then let's see if I'm maybe missing something basic. Okay, so and then HSS prime, SS prime is.
But you are using hybrid 1, so that will be that reprogrammable, right?
Yeah, so I think I wrote hybrid 1 in words, so that was a little bit.
Yeah, exactly.
Yeah, I think so hybrid 1 is probably not only giving A access to HSS prime, but I guess it's also using HSS prime here. And I think the argument that we gave using the theorem would still work, right? Because you can, yeah, if you knew SS prime, you could already extract it. So the outputs cannot be very different.
No, but the rename thing is just HSS prime, SS prime, not first detail.
No, it's renaming W to R, I think. Let me write it down. I think it's renaming W to R, and then HSS prime is an independent. Yeah, no, I think you're right. Yeah, probably, because otherwise it doesn't make sense, right? Yeah, okay. So because HSS prime is an independent uniform bit, so its distribution is identical to that of R. Okay. So this is kind of where the fact that we replaced, the way we defined HSS prime was we made it uniform and independent of everything else. So we're using that fact now. So instead of using the randomness that was specified by HSS prime, if you just use a different randomness here, it's okay because yeah. So the distribution stays essentially the same. Yeah. Horizont. Sorry, say it again.
R is uniformly sampled in 0 and 0. Oh, that makes it. Okay, that makes it equivalent to HSS prime.
Yeah, but what I'm a little bit concerned about is that HSS prime.
Yeah, HSS
A has
at SS prime.
Yeah, so A has access to HSS prime, so that's what worries me a bit, because
But I'm wrong.
no, I think wait, what did I do? It's just sending R. No, I think it was replacing all of W with little r. I don't think it was replacing HSS with, because you're sending W, right? And here instead of W, it's sending R. So I think it's not. I think it was actually just replacing all of it with R. And now the distribution that A sees is going to be essentially uniform, because now it's arguing that this HSS prime at SS prime was uniform. So whether you XOR with the bit or not, it will not make a difference. But this does not look very.
I was thinking that these oracles must be equal at z equal to s and z minus s.
Yeah, that's what I was also. I mean, the oracles are going to be the same. That's not a problem.
So at the SS prime, all the reprogrammed oracles must give the same kind of output.
Yeah.
So if you replace whole omega by r, then you have to argue differently.
No, but the adversary doesn't see. It only sees the bit r, right? So it doesn't. Yeah, so this maybe you can think about if it's correct or if there's some argument that needs to be made, because
So should we be worried about like bit B as well? I thought that just if SS prime gives you random answers, it's fine.
give me a second. Actually, what did we do? Is it? But A still has access to HSS. So if it's 0, you
That is true for hybrid 1 and 2 both.
get. Yeah, that's what I'm trying to see, because yeah, so in the second step we'll get oracle, and now yeah, I think I'll need to think about it more carefully. I'm actually not fully convinced now that this is. Yeah, my main concern is that you still have access to HSS prime, right? The oracle HSS prime.
That is true in both oracles.
Yeah, but the difference is that you're given. Yeah, I don't know if I have an attack. My concern seems to be that in one case you're XORing with the HSS prime itself, right? Like for example, suppose I chose delta to be all zeros, okay? So then B dot delta would be 0, right? So it will make, whether or not B is 0 or 1, it will make no difference, right? You'll never add anything, right? And then if I somehow could query HSS prime at SS prime, then I could distinguish, right, whether you're giving me a random bit or whether you're giving me HSS prime.
But HSS prime is also random.
Yeah, but there are two, whether they're independent random bits or are they the same random bit, right? Because A gets access to the oracle itself, right? So suppose magically I could query at SS prime. What I will do is I will check is the second message. So let's call this, M2 and this is M1. So I'll check whether M2 matches HSS prime at SS prime. And this will allow me to distinguish the two hybrids. Of course, I can't query at SS prime because that will violate. So I am guessing the statement is correct, but
They are random, so they will not match.
no. But in this case, if delta was 0, B is 0, so omega will be what? So if delta is 0, what will omega be?
Yeah, there will become 5 or something.
Huh?
That will be
You'll get.
f prime plus page 1.
Oh! I think I kind of. Okay. No, I think you're right. Okay. I think it's fine. I messed up. I was thinking that omega is. Yeah, okay. I think this is the part that I got wrong. There's no SS prime. I think then it's fine. Okay, then it's okay. So the point is that whether you are XORing with H at SS prime or you're XORing with or you're just outputting some little r, is the same because the adversary never sees HSS prime, because we already replaced the evaluation of HSS prime by some independent uniform bit.
And B was also random.
Sorry.
for-
B,
Sorry, yeah.
that doesn't matter. That's what we are testing actually. So it should hide it completely. Yeah. Sorry about the confusion. Okay. Did you understand what the confusion was and what the solution was?
Yeah, maybe you tell again.
Okay. So the confusion. So what I had done was I had earlier written this, and this was wrong. It was my mistake. I'm sorry. So I had written HSS prime. Okay. And then I was trying to argue that P1 would be identical to P2. Okay, but that's not true, because with exponentially many queries, at least you can show that P1 will not be equal to P2. And why is that? Because if you look at hybrid 1, right, and you assume that it was SS prime instead of H, and you had A send delta 0, all zeros, okay, then omega would be exactly HSS prime. Like it would be U, right? So yeah, suppose this was SS prime, which was what I was thinking, here. So this would just be U, right, from the definition, and this part is 0, right, because I send delta to be 0. So the output that hybrid 0 would see is U, right, and the adversary has access to the oracle, right? So this also evaluates to U, right? Correct? However, in hybrid 2, you were sending little r, and little r is independently sampled, correct? So when you check, in one case M2 would be little r, in the other case it would be U, so they'll not match. Okay, so you cannot claim that P1 would be equal to P2, but of course that's not what is happening, because you're not sending H with SS prime. So W is defined to be H SS prime XORed with this bit, and the adversary actually never sees the evaluation of HSS prime. That was the whole point of doing the first hybrid, right? Because we removed the evaluation of HSS prime from the view of the adversaries entirely. Okay, is that clear? So sorry for the confusion, but I think it's also good because it kind of forces you to look at what the hybrids are doing a bit more carefully. Okay, yeah, sorry for the delay. Any questions? Is it okay? Okay, so we proved that P0 is negligibly close to P1, and we prove P1 equals P2. Now let's do the main thing, which is to show that using hybrid 2, one can extract. So if you win in this hybrid 2 with non-negligible probability more than half, then you can extract SS prime. Okay, so that's the main objective that we're going to prove now. Okay. Lemma 4.11. Okay. So we set up some notation first. Okay. So fix A little r delta to canonical vectors SS prime. Okay. And then they use this slightly wonky notation, which is H minus SS prime. So this is like what they call a partial random oracle. I don't think it's very standard notation, but okay. So this is, it's basically specified at all points except SS prime. So specified at all points. Okay. And then definition pi 0b and pi 1b are projectors okay, on Hilbert space B, okay, defined as follows. Okay. So these projectors are going to look a little bit mysterious. We kind of already mentioned them in the tech overview, but the formal statement I skipped of the theorem that we'll use. Okay, so the analog of the theorem that we used for showing P0 is the same as P1. We need like a similar theorem. So maybe I'll state it next time, but for now let's just define these projectors. So the projectors are as follows. So P0B runs algorithm B on input the description of A with Oracle access to H0 SS prime. Okay. So H0 SS prime is, I think, this one. Okay. So it does this. It measures B using little r and identity minus little r. That seems a bit weird. Should probably be BB, not yeah, this is probably little b. Because you're checking that. Wait, that seems a bit odd. Give me a second. Let me double check. What do you guys think it should be, R or B? Why?
It doesn't know what it is.
Yeah, but they're supposed to output B, right? I think even syntactically it should be BB, right? Because
Yeah, maybe it will be okay.
yeah, I think it should be BB. Let me check if I messed up. Man, this paper's okay. Let's see. Yeah, it says R. Okay, so except on input SS radar, it measures if the outcome is R, then it undoes all the computation.
Don't know what.
But that doesn't even make sense. Wait, is little r a bit, or no? It's an n-bit string, and B is supposed to output home, and even syntactically it's not correct. What are they writing?
No, but one string will correspond to one outcome, right? We can say that the bit is 0 or 1, depending whether.
One string will correspond to one outcome.
Yeah, if you measures get R, and if you get set, then you will output it.
So I know. Wait, what are you saying? I thought B. It's looking at the output of B and C, right? B and C are supposed to output bits.
But how do you explain this? Pi 0B runs B on input, so who is doing this experiment?
That's the projector, right? So you're saying that you got this, like we discussed in the tech overview, you got the bipartite state here, right? And then once you have the bipartite state here, instead of running BC directly, it's describing what the projector would do. So they're related, they're not different. But he's just saying that I can define a projector on the Hilbert space B. And the way I define it is that, I will give in addition this description of A.
Oh, okay, so it's not pi 0B runs B. Pi 0.
Yeah, it is a projector. So the projector is like, I'm giving you a description of the projector.
The description of the projector. I read pi 0B runs B.
Yeah, okay, yeah. But I'm just describing the projector. So you run, but that's what I actually was saying, but okay. So you run B on this input, you have Oracle access to 80SS prime, and then you measure. Yeah, I think they meant to write BB. I think it's they just messed up. It doesn't make sense otherwise, because they're checking whether you're given the 0th oracle or the first oracle. So
That
I
is
guess
what
it
the
is.
output, right?
Yeah,
Will
yeah.
be the output.
Yeah, you're basically measuring a computation. You're checking if the outcome is B or not B.
That is true, but they don't know this projector.
Yeah, you're given the algorithm B. You run the algorithm. It will produce an output. You check whether the output matches. You're basically making a circuit, right? So you're basically drawing the circuit. You're saying you do B, then you do this projection on BB.
Yeah, exactly.
Depending
How
on
do
yes or
you
no.
You are doing this projection. That is what I'm trying to ask.
It's the environment.
So this is done by the challenger.
Yeah. So now, okay, maybe.
Oh, this is done by challenger.
Or like it just
I mean, basically, what you're doing is you're going to use ABC to produce a new adversary A prime, B prime, C prime. That would. Yeah, and then you would basically mathematically argue that the success probability of this is the same as something you would express using pi 0, pi 1. So it will just be a mathematical expression at the end of it.
So if
And-
challenger is doing this, then everything is possible. You can perform measurement BB, BC, or BB, whatever.
Yeah, but no, maybe it has to be local. Yeah. Yeah, let's see how it's used. Yeah. Because yeah, I think that they just use it to bound certain things. I don't think they use it to, like, the construction for A prime, B prime, C prime appears later, and you're basically able to argue that you can express in terms of pi 0b and pi 1b the success probability of the.
That will let.
Yeah. So that's essentially, you're basically, yeah. So in a sense, you can think that you're rewriting the challenger as wait, what was your name again? Shreyas, as Shreyas was saying. Yeah. Okay, good. So you measure B using PB and identity minus PB. Okay, and then you run B backwards. Right. I think this we discussed as well when we were doing the tech overview. Backwards. Right. Okay. So this is pi 0. And then pi 1 is the same as pi 0, except yeah, you want to check. Yeah, actually, maybe let's just do this instead of B, because this was B actually, right? So maybe I can just write it as little b. Yeah, maybe let's not write it as B. So you do this 0, 0. Okay, and then if you're using, let's use another color. And if you're using pi 1b, the definition of pi 1b would be, essentially the same thing, except that you now check 1, 1. And you use Oracle H1. Right. Okay, so I think that allays your concerns. That was I think I was kind of missing the main point. Because when you're defining pi 0, you'll just use 0, and when you're defining pi 1, you'll use 1. So you don't need to know B independent of what was happening. Yeah. Good. Yeah, sorry, I think I was just trying to wrap my head around why they were using R instead of B. So I kind of got fixated on that. So good. Yeah, let's see if anything breaks after this. And now we're going to use. Okay, so this was 1 and 2. So 2 was for pi p. That's good. And now we're going to use essentially the same sort of. Yeah, I think now we can get rid of this, right? Now we don't need hybrid 0, since we proved that we only need to care about the last hybrid. Let's do that. Okay, so you run B backwards. Okay, and then we define phi I to be a set of eigenvectors pi 0b plus pi 1b by 2 with eigenvalues this one's lambda I. Okay, and one can define also pi 0c and pi 1c analogously, where instead of, so register B now becomes C, okay, and adversary B becomes adversary C, right? So it's essentially the same idea. And now we let psi sub j, okay, this is the same thing, eigenvectors of pi c0 plus pi c1 by 2, okay, and the eigenvalues are going to be mu j. Okay, and we're using a different index, I guess, because the range could be different. Okay, good. I think we can, yeah, we're getting to a good point where we can pause. So we're going to write phi sub bc. Okay, so let phi sub bc be the state prepared by A, okay, and we write it as, without loss of generality, alpha ij phi I on B tensor psi j on C. Okay. So it's a bipartite state, right? I can write it in terms of eigenvectors in B and C, and the eigenvectors that I've chosen are coming basically from these measurements that we had defined. Okay, so some of the measurements right here, pi 0, pi 1, and similarly pi 0, pi c. Okay, and as you can probably kind of see that this is like very similar to the form that we had in Jordan's lemma, right? Like we were saying that we analyzed what the eigenvectors will do and when they're orthogonal and so on. So we'll use that fact. Okay, I have 1 minute. So let me state a lemma that is a bit technical, and we'll see whether we'll have the time to prove it. But there's a lot of magic happening in this lemma that we need to sort out at some point. Okay, so over the randomness of A SS prime and the oracle except at the value at SS prime, for every polynomial P, there exists a negligible function such that with overwhelming probability it holds that sum over j or sum over I lambda I minus half is at least 1 by p, and mu j minus half is at least 1 by p as well. Okay, so if you look at indices for which the eigenvalues are bounded away from half, okay, by some factor, then the weight that this specific state assigns, okay, on those indices, right, that correspond to the projectors, these eigenvalues being bounded by half, is at most this negligible function that we chose. Okay, this is negligible in n, but okay. So I guess we'll have to stop now, but we'll continue with the. So we'll assume this lemma for the moment, okay, and then we'll complete the proof next time. And the proof of the lemma we can see, like if people are still interested, we can do it, or maybe I think it's better to do it as an assignment or something. But yeah. So yeah, so I think let's pause here for the day and we'll see. So yeah, in the next class we'll be able to apply Jordan's lemma and use the facts that we had used today together with this to argue that you will not do better than half plus negligible. And the extraction thing happens in this one. Like you can show that if this is not satisfied, then you can extract, you can break the monogamy of entanglement game. So that step happens over there. Okay, thanks you guys.